In this lesson, we'll be looking at Karnaugh maps, or KMaps for short. Now, in the previous lesson, you probably had some experience with Boolean algebra, and you encountered different identities and different rules. Now, KMap is a visual representation of a truth table, and it makes it a lot more easier to come to a simplification or a representation of a truth table or a logic circuit without going through all that complexity that comes across with Boolean algebra. Now in the exam, you will need to create a KMap from a truth table. You should be able to work out what an expression is, and you need to identify the different patterns that might occur in a KMap. For example, grouping bits together. But before we begin, it's always useful to go through some key terms. So do pause the video and go through these particular ones. You should understand that when we talk about sum of products, we basically are talking about a Boolean expression which contains and or terms, which basically is most of them. When we talk about gray codes, these are the ordering of binary numbers such that the successive numbers differ by a 1-bit value only. For example, 00 and 01 are successive, they're one after the other, and the difference is only 1 bit. 0 to 1 is just 1-bit difference. And then the next set is 3, which is 1 1, and next one is 1 0, which is a 2. So the difference between 3 and 2 is also 1 bit. Now these gray codes come in handy when we create KMaps, because the headings for the columns and the rows depend on these gray codes. So ideally you would always start with 0 0, and then you go to 0 1, and then have 1 1 and 1 0. That's the normal convention. Now if you have like two basic inputs, A or B, then A is 1 and not A is 0, and B is 1 and not B is 0. And if you end up with two inputs like A, B and C, D, then A, B will be 1 1 and not A, not B will be 0 0. We'll go through gray codes in a bit more depth as we go through KMaps. And finally, KMaps, these are just a method for simplifying logic statements and logic circuits, and they use gray codes which start from 0 and have a 1-bit difference for the next successive term. And I cannot stress the importance of using gray codes. Try to memorize the process. It starts with 0 or 0 0, goes up to 0 1, then 1 1, then 1 0. That's the order. Remember that order for the headings and you will never get KMaps wrong in the exam. Now let's delve a bit more deeper into KMaps. KMaps were developed to help simplify logic expressions and circuits, which can often become very complex. And they have their own set of rules. For example, the values along the top and bottom, so that basically means the column headings and the row headings, they follow gray code rules. So you start with 0, which in this case will be not A and not B, that's 0, and A is 1 and B is 1. So the difference between not B and B is 1 bit, and the difference between not A and A is 1 bit as well. So they follow gray code rules. Now the second rule is that we only take into account the cells that contain 1 and we ignore the ones that have zeros in them. The third rule is that we can group these ones in a row or in a column or in a rectangle, and these groups of ones must contain an even number of ones, and these ones should go up in groups of 2s, 4s, 8s and so on. That's the fourth rule. And when we take these groups into account, we go with the largest group possible. So for example, if you've got 4 ones, you can't make 2 groups of 2s, you've got to make 1 group of 4. The next rule is that the groups can overlap within the previous rules. So you might have a situation where you've got 2 ones going across and 2 ones going down, and one of those ones is overlapping in both groups, because you can make a pair which goes across and a pair that goes down. Now the image on the top right highlights this. You can see 2 ones going across and 2 ones going down. The one in the corner is overlapping in both. The next rule states that single values can be regarded as a group even if they cannot be combined with other values to form a larger group. And the final rule simply says that the final Boolean expression can only consider those values which remain constant within the group, that is, either remain a 1 or a 0 throughout the group. So if you take the first horizontal group, which is highlighted in red, you can see that not A is constant all the way across. However, not B and B basically end up cancelling each other out. So that red group resolves itself to not A. So if you look at the vertical group that's highlighted in green, you can see that not B is constant all the way through, and A and not A basically cancel each other out. So you end up with not B. So the overall expression for that K-map that you see in the corner is not A or not B. Now let's look at a worked example in a bit more depth. So a question might be something like this: produce a Boolean expression for this particular truth table. Now you can do it via Boolean identities and Boolean rules, or we could use a K-map. So the truth table is given to you. It's got two inputs, A and B, and you've got an output. Now you can see from the truth table that the output X is not 1 when both of the inputs are 1, otherwise all the outputs are 1. And we can write this, which basically is a NAND gate, as saying not A and not B, which is 0 and 0, gives you a 1, or not A and B, which basically is 0 and 1, gives you a 1, or A and not B, which is basically a 1 and a 0, give you a 1. So all the ones are represented in that Boolean expression. Now you could use Boolean identities and rules to simplify it to not A or not B, or you could use a K-map. And what we normally do is we draw grids, and we start with 0, so that's not A, and then we write down A. And similarly at the top, we write down not B, which is a 0, and B. So these are your column and row headings, which are related to the inputs. Now for the output, we just look at the output wherever there is a 1. So we know that when not A and not B, which basically means A and B are 0, the output is 1. So in that particular cell, we write 1. Similarly, we go to the next line of the truth table, and we know that not A and B results in a 1. So we just go across and write a 1 there, and then we fill the K-map accordingly. And once this is all filled up, we can then group the ones in 2s or 4s. In this case, there's 2 pairs, one going across, one going down. This is exactly the same example we just discussed on the previous slide, and we resolve it down to not A or not B. And this is a lot more simpler than working via Boolean identities and Boolean rules. So let's look at another example. Here's a truth table for you, and you need to simplify it using a K-map. The rules are on screen as well, and I have taken the liberty of writing the expression down for you, which includes all the ones. So we know that when A, B, and C are 1, then the output is 1. And similarly, when not A, B, and C are present, then the output is 1. Or A, not B, and C, the output is 1. And the final output is A, B, and not C, which gives you a 1. So there are 4 ones in the truth table, and hence there are 4 parts in the expression. Now you need to create a K-map. And how do you do a 3-input K-map? Well, you can take one of the inputs like A to the side, and the other will be B and C. So you can split it that way. If you get a 4-input expression like A, B, C, D, you then group A and B on one side and C and D on the other side. And you can choose which side you want these to be in, but you've got to follow gray code rules. That means start with 0, 0 and work your way up. Pause the video and have a go at this, and when you're ready, press play to see the solution. Okay, hopefully you got an answer that looks something similar to the one on screen. So you've got A on the left hand side, you start with not A, and you've got A on the second row, and on the top you've got not B, not C, because that's 0, 0, and then you work your way accordingly. And then you've populated it, and you found out that there were 3 pairs of 1s, and you've highlighted those, and then you simply resolved those, and you ended up with A and C, or B and C, or A and B. And the way it works is that if you look at the green highlighted pair, you can see that A is constant, and on the top you can see that C is constant, so A and C come out from there. So the not B and B cancel out in the green pair. Similarly, if you look at the red one, you can once again see that A is constant, and this time on the top B is constant, but C kind of cancels not C out, and you end up with A and B. And similarly in that vertical group, you can resolve that to cancel out A and not A, so you end up with B and C. Now let's look at another complex example. This is using 4 inputs. That's going to be the extent of what you'll probably resolve in the exam, A, B, C, and D, and the output is X. Now, you can see there are about 7 ones in this truth table, so the sum of products for each one is listed for you to make it easier for you, so you could create the initial Boolean expression that way. Rules are on screen as well, so split the input into sets of 2, so you can do A, B, and C, D because there are 4 inputs, so you can have A, B on the left hand side and C, D on the top. Create the K-map for this and see if you can work out the solution through applying the rules. Pause the video, and when you've got the solution, continue on to check it. Hopefully you got something like this, and you've simplified the expression to not A and not B, or not C and D. If you got a different expression, then check whether you've got the gray code rules at the top. Often I find that students don't start with 0, 0, and they probably start with 1, 1. For example, they have A, B on the front, and then they probably have not A, not B, or something like that. So the difference between A, B, which is 3, and not A, not B, which is 0, is more than 1 bit, and that doesn't follow gray code rules. Now you could probably have A, B on the left hand side and C, D on the top. Chances are that you'll probably have a different shape, but the expression will simplify to not A and not B, or not C and D. Now there's variations of K-maps because we could probably have A, B at the front, and then A and not B, and then not A, not B, and then not A and B. So you could swap the headings to have successive gray codes. You might end up with different variations of ones. So it's quite useful to learn a few techniques that can help you out. Now look at the first K-map on the top, and if you try to resolve it, you can just see that you've got a group of 8. Now if you resolve that group of 8, you can probably just see that D is constant at 1, and that's about it. Everything else just cancels itself out. Now this isn't the solution to this particular K-map because you can probably see that 1 just above that group of 8, which allows you to make an extra pair, and then you could probably solve it. If you want, you could have a go at solving this, and you'll find that the expression will include D plus another term, which in this case probably is not A, not B, and not C. Now the one on the bottom right, where you can see that you can make a group of 4 ones on the left and 4 ones on the right, but because this is a cyclical approach and you can have the headings interchangeable, you can group those 4s in the corners as one group of 8, and then you can resolve it all together. You don't need to do 2 groups of 4. Remember, the biggest group matters. So if you got a column of 1s on the left and a column of 1s on the right, you can group both of them together as 8. So it kind of looks like a circular approach rather than just 2 columns of 4s. So in this case, if we try to resolve it, you'll probably see that the only thing constant is not B, everything else just cancels out. So just like a vertical cylinder, you can also create a horizontal cylinder. That means that if you get a 1 on the top and a 1 on the bottom, you can group them together as a pair. Or if you've kind of got a couple of 1s on the top and a couple of 1s on the bottom, you can group them as 4s. Now if you look at the first K-map on the top right, you can see that there's a 1 on the top and 1 on the bottom, so we're going to create that circular horizontal cylinder, and that pair can be resolved. So in this case, the output is going to be not A, B, and not D, because the C and not C cancel out. And similarly, if you look on the bottom right hand corner, you've got 4 1 values which can be combined, and these are right in the corner, so we can apply both horizontal and vertical cylinder rules, and all of those 1s can be grouped together as a pair of 4, and in this case we can resolve that, and these resolve to not B and not D, because the not C and C cancel out, and the not A and A cancel out. So hopefully that gives you a better understanding of how K-maps work, and they're actually pretty simple to resolve. The best thing to do here is to try some examples out. On screen you've got a few questions. See if you can resolve these and simplify these using K-maps. See if you can create a logic circuit based on the simplified Boolean expression using just AND or OR gates, and that will give you a better understanding of how logic circuits, truth tables, and K-maps are interlinked. One of the advantages of using this approach is that instead of using a multitude of gates, we can simplify the expression and use less gates, which means that we're going to save money by buying less and still getting the same logical output. It also makes circuit design more efficient because we can then pack a lot more gates and transistors on a particular chip rather than just expanding and creating more complex logic. And that's the end of today's lesson. Hopefully you understand the purpose of K-maps and what the rules are of creating K-maps and how to use K-maps to simplify Boolean expressions. This is a very common question in exams, and normally you end up scoring between 6 to 8 marks. So do spend some time in understanding it. And as usual, if you have any questions, do get back to me.